Hello guys, and welcome once more to this new video into our YouTube channel. So in today's video we are going to be solving a very interesting question on further complex numbers. So the question is divided into two parts, the A part and the B part. The A part reads: solve the equation 0 to the power 5 equals 1, giving your answer in the form r open bracket cos theta plus I sin theta, where r is greatly greater than 0 and negative pi is less than theta, and theta on its own is less than or equals to pi. Hence, show that cos 2 pi divided by 5 plus cos 4 pi divided by 2 equals negative a half. In the B part, we have been told that given that omega equals cos theta plus I sin theta, find the modulus and the argument of 1 plus omega. In the next part of the question, we are asked to expand 1 plus omega raised to the power n, where n belongs to the set of all natural numbers in ascending powers of omega. And hence, we have been told that in the next part of the question, we have been told that hence, using the moivre's theorem or otherwise, prove that the sum of n factorial cos r theta divided by n minus 1 factorial n times r factorial, r moving from 0 to n, equals 2 raised to the power n cos raised to the power n cos of theta divided by 2 raised to the power n times cos of n theta divided by 2. Let us actually launch into the solution of this question. So in the A part of the question, we are asked to solve the equation 0 to the power 5 equals 1, giving an answer in the form r open bracket cos theta plus I sin theta, where r is greater than 0 and negative pi is less than theta, and theta on its own is less than or equals to pi. So the first thing we are going to do is simply what? We are first of all going to let z be equals to r open bracket cos theta plus I sin theta. And we also know that one can still be written in the form cos 0 plus I sin 0. Why am I doing this? Why am I putting this condition? I'm putting this condition because what are we trying to do? We are trying actually to equate these two expressions so far. That is, letting z to be equal to this expression and putting 1 to be equal to cos 0 plus I sin 0. I'm simply going to apply the moivre's theorem on this z, and at the end I'm going to equate it with the expression of 1 in terms of the trig function, that is cos 0 plus I sin 0. So the first thing which I'm going to do, I'm first of all going to apply the moivre's theorem on this complex number z, that is r raised to the power 5 times cos 5 theta plus I sin 5 theta is going to correspond to the moivre's theorem which are applied on the complex number z here, to be equals to cos 0 plus I sin 0, what? Because these terms still bring us back to 1 again, from which we also know that sin theta and cos theta are periodic functions with period 2 pi, from which I can therefore write this expression of cos 0 and sin 0 as cos 0 plus 2n pi, then plus I sin 0 plus 2n pi. This z term remains the same. That is when I apply the moivre's theorem, which I can further simplify because I know that cos 0 plus 2n pi still come back to cos 2n pi. Similarly for sin 0 plus 2n pi. At this level, what I'm going to do, obviously where n here belongs to set of all integers so far, what am I going to do at this level? I'm simply going to further simplify again, to simply factor out 1 from this expression, which will come back to the same thing. Why am I doing this? I'm doing this because at the end I'm going to equate the corresponding entries, that is r raised to the power 5 is actually going to be equals to 1, and 5 theta is actually going to be equals to 2n pi. Similarly, it works same for sin theta, that is 5 theta is actually going to be equal to 2n pi, where n here, take note, belongs to a set of all integers. And from which, further simplifying, I can therefore obtain r to be equals to 1 and theta to be equals to 2n pi divided by 5. I still take back again where n here belongs to a set of all integers so far. Now what am I going to do at this level? I'm simply going to obtain the values of n, okay, for which, having the values of n, I can therefore obtain the value of theta. Why am I doing this? I'm doing this because, remember, we want this complex number z, in fact, because I only have r which actually equals to 1. We are simply going to obtain these values of theta, and for us to obtain the values of theta, we need the values of n, okay. And how can I obtain these values of n? By simply respecting this condition of theta. That is, we know that theta is obviously, as I said, n belongs to the set of all integers. We know that theta is greater than negative pi and less than or equals to pi, from which, putting these values of theta, which is in terms of n, we are going to have 2n pi divided by 5 greater than negative pi less than or equals to pi, from which further simplify and get n to be greater than negative 5 divided by 2 and less than or equals to 5 divided by 2, from which further simplifying again I get n actually to be greater than negative 2.5 and less than or equals to 2.5. But remember, very important, since I've obtained the values of n here, I'm simply going to get there for the values of theta here with the corresponding values of n, where n here belongs to all integers. So in this interval, I'm going to look for the values of n which belongs to the set of all integers and substitute it inside this expression of theta, And having the expression of theta, it means I can therefore obtain these values of, I can therefore obtain the expression of the complex number z, because I already know r here is actually equals to 1. From which inside this interval we can conclude that n is actually going to be equals to 0, 1, 2, -1, and -2. Why? Because inside this interval we can have 0 as an integer, we can have 1 is inside that interval, we can have 2, we can have -1, and we can as well have -2. Having these values of n, we can therefore get the values of theta, because theta is in terms of n so far. So from which we can say that when n equals 0, theta is actually equals to 0. So if you put n equals 0 here, we are going to have theta equals to 0. When n equals 1, we are going to have theta to be equals to 2 pi divided by 5. When n equals 2, we are going to have what? Theta to be equals to 4 pi, that is 2 times 2 times pi, that is 4 pi divided by 5. When n equals -1, we are going to have theta to be equals to -2 pi divided by 5. And when n equals -2, we are going to have theta to be equals to -4 pi divided by 5. From which, having these values of thetas, we can therefore come inside the expression, that is the roots of the equation 0 to the power 5 equals 1 are going to be respectively z1, that is when n equals 0, theta equals 0, and obviously as I said, r remains 1 here. So z here is actually going to be equal to 1 times cos 0 plus I sin 0, because theta equals 0 when n equals 0. Move forward again, when n equals 1, we get the second complex number, that's the second root, which is actually going to be equals to cos 2 pi divided by 5, then plus I sin 2 pi divided by 5, because remember, as I said, r here remains 1. And obviously we take then, when theta equals 4 pi divided by 5, we get the third root of the equation z to the power 5 equals 1 as cos 4 pi divided by 5 plus I sin 4 pi divided by 5. We get the next root when n equals -1, that is when theta equals -2 pi divided by 5. We get the next root of the equation z to the power 5 to be equals to 1 as cos of -2 pi divided by 5 plus I sin 2 pi plus I sin -2 pi divided by 5. And finally, when theta equals -4 pi divided by 5, we get the last root of the equation z to the power 5 equals 1 as z to the power as cos of -4 pi divided by 5 plus I sin -4 pi divided by 5, which actually correspond to the root of the equation z to the power 5 equals 1. So in the next part of the equation, we are asked to show that cos of 2 pi divided by 5 plus cos of 4 pi divided by 2 equals -1/2. So we know that the sum of the roots of the sum of the nth root of any complex number is actually equals to 0. Obviously, remember, the sum of infinity of the fifth root therefore of unity is actually equals to 0, because in the a part of the equation we obtain all the fifth roots of unity. Okay, so far we can therefore sum all of them. That is, we can sum z1, z2, z3, z4, and z5. Why? Because these were the roots of the equation z to the power 5 we obtained so far. And since we know that the sum of n roots of any complex number is actually equal to 0, in this particular case, this n here is going to take the place of 5. Why? Because in the a part, we solve the equation 0 to the power 5 equals 1. So in this particular question, we can therefore say the sum of the fifth root of unity is actually equals to 0, for which we can therefore sum all the different roots we obtained in the a part of the equation to be equals to 0. So saying that, it implies we can say that the real part actually equals, because if the complex number equals 0, it means the real part equals 0 and the imaginary part as well equals 0. But in this particular question, we are going to say that the real part of the complex number of this complex number, because this is going to give us the complex number so far, because z1, z2, z3, z4, and z5 are complex number. So saying that the sum of those complex number equals 0, it means we can still say that the real part of the complex number is actually equals to 0. So saying that, it implies, in the first place, first of all, know that let's first of all recall all the different roots we obtained in the a part, that is z1, z2, z3, z4, and z5. Saying that the real part of the complex number, that is the real part of the sum of this complex number equals 0, it simply implies we are going to have cos 0, which is the real part, then plus cos of 2 pi divided by 5, then plus cos of 4 pi divided by 5, then plus cos of -2 pi divided by 5, then plus cos of -4 pi divided by 5 to actually be equals to 0. Or obviously, further simplifying, that is, we know that cos theta is an even function, that is cos negative theta equals cos theta. That is, everywhere we have cos of -2 pi divided by 5, we are simply going to replace it with cos of 2 pi divided by 5, and similarly, where we have cos of -4 pi divided by 5, we are still going to obtain cos of 4 pi divided by 5. and we know that cos 0 is actually equals to 1. So further simplifying, we are going to get what? That is implementing this condition, that is cos theta being an even function. We are going to have this, as I said, from which further simplifying, we are going to have cos theta, cos 0 which actually goes to 1. So that is 1 plus 2 cos 2 pi divided by 5, because we have cos 2 pi divided by 5 plus cos 2 pi divided by 5, and similarly plus 2 cos of 4 pi divided by 5, because we have cos of 4 pi divided by 5 plus cos of 4 pi divided by 5, which give us plus 2 cos of 4 pi divided by 5. With further simplifying, we therefore get cos of 2 pi divided by 5, then plus cos of 4 pi divided by 5 to be actually equals to negative a half, and which was actually what was required for us to prove in the next part of the equation. So in the next part of the equation, we are being told that omega equals this, that omega equals cos theta plus I sin theta. We are asked to find the modulus and the argument of 1 plus omega. So you clearly agree with me that in the equation as it was given, omega was given to be cos theta plus I sin theta. In the first place, we are first of all going to find 1 plus omega, because 1 plus omega is actually going to correspond to our complex number, which we are going to find its modulus and its argument. So 1 plus omega is actually equals to 1 plus cos theta plus I sin theta. In the first place, we are first of all going to further simplifying that we are going to break it into its real part and its imaginary part. That the real part of the complex number 1 plus omega is actually 1 plus cos theta, and its imaginary part actually the sin theta, actually, for which we can therefore move forward and get the modulus and the argument of 1 plus omega, because we clearly obtain the complex number 1 plus omega. Modulus, we know that the modulus is what? The modulus is actually what? The square root of the real term of the complex number squared plus the imaginary part squared. For which further simplifying, we are going to have the square root, we are going to have 1 plus omega equals the square root of 1 plus, that is, if you expand this square, expand this bracket, we are going to have 1 plus 2 cos theta, then plus cos squared theta. If you simplify it, then plus sine squared theta. From which further simplifying again, we get the modulus of the complex number 1 plus omega to be equal to the square root of 2 plus 2 cos theta. Why? Because we know that cos squared theta plus sine squared theta give us 1, and then 1 plus this one give us 2, and then we are going to have 2 plus 2 cos theta. Okay, from which we know that, in fact, we know that what we are going to, in fact, what are we going to do? We are simply going to completely break down this interior expression here into something good, which is going to help us, obviously. So we can move forward to trig identities. That we know that cos 2 theta is actually equals to 2 cos square theta minus 1. For which inside this expression we can simply do what? We can simply obtain the value, we can simply obtain cos theta. That is, we can simply deduce what is cos theta. Because if cos 2 theta equals 2 cos square theta minus 1, it means cos theta is actually going to be equal to what? 2 cos squared theta divided by 2, then minus 1 simply. Why? Because if I put theta here I'm also going to have theta divided by 2. It's like this theta here is 2 times this other one here. We actually come back to the same thing as this one, because if we do 2 times theta divided by 2, we are going to get back theta again. So from which, having the values of cos theta, we can therefore come forward and get 2 cos theta. Because why? The thing is that I'm trying to obtain this expression here, this bracket expression. That is, we can therefore multiply 2 inside this expression. That is, if we multiply 2 on both sides, we are going to have 2 cos theta to be equal to 4 cos squared theta divided by 2, then minus 2. From which I can therefore impute again these 2 here. That is, I can therefore come forward and put this. That is, impute this 2 cos theta inside this square root value, which I want to obtain as well. That is, the modulus of the complex number 1 plus omega is therefore going to be equal to the square root of 2, then plus 2 cos theta actually correspond to 4 cos squared of theta divided by 2 minus 2. So further simplifying it, we are going to get what we know that these 2, we're going to cancel with these 2. So we are going to get with the square root of 4 cos squared theta divided by 2, and putting the square root value, we are simply going to get what? 2 times the absolute value of cos theta divided by 2. Why? Because if we take the square root of cos squared theta divided by 2, we get the absolute value of cos theta divided by 2, obviously. From which was actually what we are asked to obtain, that is the modulus of the complex number. Because we cannot exclude this absolute value here, because if you take the square root of something squared, it actually corresponds to the absolute value of that corresponding expression. So this expression, that is 2 absolute value of cos theta divided by 2, corresponds to the modulus of the complex number 1 plus omega. Let us therefore obtain the argument of the complex number 1 plus omega. Obviously, we had 1 plus omega that we already obtained the complex number. So the only thing we need to do is actually to obtain the argument of the complex number. But now, look at this complex number. The complex number actually, the real part actually is positive. The imaginary part as well is positive. So the argument of the complex number 1 plus omega is actually going to be equal to tan inverse of the imaginary part divided by the real part value. That is tan inverse of sin theta divided by 1 plus cos theta. From which we can therefore move forward again, as I said, and use back trig identities to further simplify this interior expression here. Very important, because we cannot leave this expression as such. We must go forward and simplify it completely, as we did for the case of the modulus. So obviously, as we did here, we know that cos theta equals 2 cos squared theta minus 1. We can therefore say that cos theta is actually 2 cos squared, as we did here. It's actually 2 cos squared theta divided by 2 minus 1. From which we can therefore move forward and therefore use also the fact that cos 2 theta equals to 2 sin theta cos theta, which is still a trig identity. And from which we can therefore say that from this expression, sin theta is actually equals to what? 2 times sin theta divided by 2 times cos theta divided by 2. Why? Because it's the same thing we did at this level, the same thing as we did for the cos one. That is, if I want sin theta, knowing that sin 2 theta equals 2 sin theta cos theta, the sin theta is in question is going to be 2 sin theta divided by 2, then times cos theta divided by 2. Because if I do 2 times theta divided by 2, I'm going to obtain theta. And saying that I multiply this term times 2, it means this one I'm going to have then 2 theta here simply. So having already cos theta and sin theta, I can therefore come inside this expression of the argument, which is in terms of sin theta and cos theta, and substitute the corresponding values there so far. So saying that in fact we can therefore come inside this expression and put the values of sin theta which we obtain. That is, sin theta will actually correspond to 2 sin theta divided by 2, then times cos theta divided by 2 divided by 1 plus cos theta actually corresponds to 2 cos square theta of 2 cos square theta of theta divided by 2, then minus 1. From which, for simplifying again, because this one is going to cancel with this other one here, for simplifying we are going to get tan, that is the argument of the complex number 1 plus omega, to be equal to tan inverse of 2 sin theta divided by 2, then times cos theta divided by 2, then divided by 2 cos squared theta divided by 2. Again, for simplifying, we are going to get what? We are going to get the argument of the complex number 1 plus omega to be equal to tan inverse of what? Tan inverse of sin theta divided by 2. Why? Because these two cancel with these two here. Obviously, take note of it. Here we have cos theta divided by 2. Here we have cos squared of theta divided by 2. So 1, that is 1 cos theta divided by 2 is going to cancel with 1 in the numerator. We are therefore going to be left with the argument of the complex number 1 plus omega to be equal to tan inverse of sin theta divided by 2 divided by cos theta divided by 2 to be tan inverse of the tan of tan theta divided by 2, because this term corresponds to tan of theta divided by 2. From which, for simplifying, we get the argument of the complex number 1 plus omega to be equal to theta divided by 2, because tan inverse of tan theta divided by 2 corresponds to theta divided by 2, which corresponds actually to the argument of the complex number 1 plus omega, which is actually what was being required for us to obtain in the next part of the equation. So in the level of the equation, we are asked to expand, that is, we are asked to expand 1 plus omega squared n in ascending powers of omega. Obviously, generally, we know that what? We know that 1 plus a raised to the power n, that is, from binomial expansion, we know that 1 plus a raised to the power n is actually equals to 1 plus na, then plus n up bracket n minus 1 times a squared divided by 2 factorial, then plus n up bracket n minus 1, then times n minus 2, then a cubed divided by 3 factorial plus dot plus a raised to the power n. This is what we are going to use, because this identity actually corresponds to a. This identity actually corresponds, is actually resembling the same thing as this binomial expansion which we want to do. That is, we are therefore going to apply this binomial expansion expression to this 1 plus omega raised to the power n. Obviously, so saying that, it implies we are simply going to replace a with omega. Simply, that is, doing that, we are going to have there 1 plus omega raised to the power n to be equal to 1 plus n omega, because I'll simply replace a with omega, and doing that all through, we are going to have this expression, because I simply replace a with omega, and from which we get this expression of 1 plus omega raised to the power n, from which was actually what was then required for us to do, because we are asked to expand this in ascending powers of omega, which is what we analyze. So the only thing you have to do here actually to identify that this one can still be broken down using the binomial expansion expression of 1 plus a, where a is actually going to correspond to omega. So we are being asked to prove that in the next part, that we are being told that hence let's prove that the sum of n factorial of cos of r theta divided by n minus r factorial times r factorial, the sum moving from 0 to n, is actually going to be equals to 2 raised to the power n cos n of theta divided by 2 then times cos of n theta divided by 2. So what are we going to do? In fact, at this level we are simply going to expand the left hand side. When I talk about left hand side, it actually corresponds to this expression here, because we want to prove that this sum is actually going to be equal to this. So we are going to first of all start with the fact that expanding the left hand side, okay, is going to enable us all to get the right hand side. So that is how we are going to move forward with this proof here. That is, expanding this left hand side, we are going to have what? Since r goes from 0 to n, we are simply going to replace everywhere we see r with 0, 1, 2, and so on until we reach n simple. So when r equals 0, we are going to have what? Cos. When r equals 0, we are going to have what? Cos 0. Then we are first of all going to have what? We are going to have n fact. We are going to have n fact. In fact, when r equals 0, we are simply going to obtain what? 0 factorial here. Are we there? 0 factorial, then times n minus 0, which give us what? N factorial. Now this n factorial is going to cancel with this n factorial. Here we are going to have 0 factorial, but 0 factorial corresponds to 1. So at this level we are going to have cos 0 as this sum when r equals 0 actually. Then plus n factorial, that is when n equals 1. We are going to have 1 factorial. Then times, we are going to, when r equals 1, we are going to have n factorial, because this sum is not in terms of n. So when r equals 1, we are going to have n factorial, then times cos theta, because r equals 1, then divided by n minus 1, then factorial, then times 1 factorial. And we do this until we reach the last value n. That is, if substitute r with 2, we have this expression. If substitute r with 3, we have this expression, and so on until we reach the last value of the sum, which is actually n. So having this expression, we can therefore further simplify it again. Why? Because we know that what? We know that n factorial is actually what? It's actually n, then times n minus 1 factorial. Okay? We are going to do that. Doing that at this level. Why are we doing this? We are doing this because in the denominator we have n minus 1 factorial. So we simply have to break this n factorial in such a way that the n minus 1 factorial in the denominator is going to cancel with one of its expression in the numerator. Because we know that n factorial is actually n times n minus 1 factorial. And we do that same for the others. For the others, we have to bring it down as the term of factorial in the denominator. That in this next expression, we are going to break, that is this n factorial is going to correspond to n then times n minus 1 then times n minus 2 factorial. Because doing this, the n minus 2 factorial in the denominator is going to cancel with the 1 in the numerator. And then, moving forward, by doing that for the others, that is, for the others, we are simply going to have what? For the others, we are going to have the same thing. That is n. For the case for the 3, we are going to have n, then times n minus 1, then times n minus 2, then times n minus 3 factorial, then divided by n minus 3 factorial, times 3 factorial, and so on until we reach the last expression, until we reach the last value. Because here I did not further simplify, okay, because I simply left it as n factorial, but you have to know that it follows the same chronology as this other one. So knowing that, therefore, we can therefore come forward and say that this sum here is going to correspond to 1 plus, as I said, this n minus 1 factorial is going to cancel with this n factorial. Is going to cancel with this n minus 1 factorial here. Then plus this other term here, that is n times n minus 1 cos 2 theta divided by 2 factorial, because this n minus 2 factorial cancel with the n minus 2 factorial in the denominator. Then plus the other, that is doing that for the other ones, that is following the same pattern. For the other values, we are going to have this for the 3 factorial case, and so on and so forth. But for this last value, obviously, we are simply going to be left with what? For this last expression, we are going to be left with n minus n. N minus n here corresponds to 0. Okay, and 0 factorial is actually 1, and this n factorial is going to cancel with this n factorial in the numerator, which we can therefore come and further simplify it by doing what? By saying that this sum is going to correspond to 1, then 1 plus what? Then 1 plus, remember, I'm simply going to write it like this, because this expression here, this cos 2 theta corresponds to the real part of the complex number omega squared, simply. Why? Because this cos theta, when I write the real part of this complex number omega, is actually what is being is what actually we must implement. Why? Because omega here corresponds is actually omega raised to the power 1, and omega raised to the power 1 is actually what? It's actually 1 times cos theta plus I sin theta. And since this expression is cos theta therefore corresponds to the real part of the complex number cos theta plus I sin theta, where r equals 1 here. Okay, and for this case, since it is cos 2 theta, it means r is going to be equals to what? It's going to be equals to 2. And since r equals 2, it means this cos 2 theta actually corresponds to the real part of the imaginary complex number omega squared. Because if you use the moivre, if you come forward with the moivre theorem, we are going to clearly see that the real part of the complex number omega squared, where omega is actually r upper bracket cos theta plus I sin theta, is going to be cos 2 theta. And doing that for the other, that is cos 2 theta, is going to correspond to the real part of the complex number omega cube. Obviously, of the complex number omega cube, because when I say omega cube, is simply what? Using the moivre theorem to come out with the fact that the real part of the complex number omega raised to the part is actually cos 3 theta, and from which we can therefore come forward and do same for the last value, that is cos n theta. Cos n theta is actually going to be equal to the real part of the complex number omega raised to the power n so far. So from which we can move forward and further simplify it again. That is, I simply came back with the expression we had in the previous slide. So we can therefore come and further simplify by simply factoring out the real part, because everything contains the real part, because this one is still a real part, but this one is a real part of the complex number cos 0 plus I sin 0. Very important, because cos 0 is actually 1, but sin 0 is actually 0. So this one here still corresponds to the real part, but of the complex number what? But of the complex number 1, because 1 is actually the complex number cos 0 plus I sin 0. So we are going to have this factoring the real part, because all these expressions actually correspond to the real part of the different complex numbers. For which I can therefore come forward and say that what? In the previous part, we proved that 1 plus omega raised to the power n was actually this expression. And if you clearly identify it, simply come back to what is inside this expression so far. You come back to what is inside this expression, because this term here is the same thing as this other binomial expression we did in the previous slide, that in the previous question. In the previous question. So from which you can therefore come forward and write therefore this sum as the real part of a complex number 1 plus omega raised to the power n, simply. Okay, and we know that, remember, we obtained something. We obtain the modulus of the complex number 1 plus omega, and we obtain its argument, and we obtain the argument of the complex number 1 plus omega. And having those answers, that is having those answers, because recall, if you still remember, we had this modulus and we have this argument. Now, seeing this expression 1 plus omega is a complex number, and we want 1 plus omega raised to the power n, we can therefore apply the moivre theorem here as well, where this term is actually going to correspond to the modulus, that is applying the moivre theorem, where r here corresponds to the modulus of the complex number 1 plus omega. And obviously we also obtain the argument of the complex number, that is 1 plus omega. That is, I simply apply the moivre theorem, that is r then times cos theta plus I sin theta. But in this particular case, theta here corresponds to what? Theta here corresponds to the argument of complex number 1 plus omega. But remember, I have here raised to the power n, so I must include everywhere, that is the r raised to the power n, where r is the modulus of the complex number 1 plus omega, and then times n times theta, where theta is actually the argument of the complex number 1 plus omega, simply. Then similarly, plus I sin n bracket argument of 1 plus omega. And remember, we had those expressions, we had the modulus of the complex number 1 plus omega, which was 2 times the absolute value of those the modulus of the complex number 1 plus omega we obtained was 2 times modulus of 2 times the absolute value of cos theta divided by 2, and the argument which we obtained was simply theta divided by 2, for which, putting those corresponding values here, we get therefore 1 plus omega raised to the power n to be actually equals to what? 2 times cos of theta divided by 2 raised to the power n, then times cos of n theta divided by 2, because remember the argument of the complex number 1 plus omega is theta divided by 2. So putting therefore all those values there, we get this expression of 1 plus omega raised to the power n. Okay, from which we can therefore further simplify it by doing what? By simply multiplying this inside this, that's by simply multiplying, that is 2 cos theta divided by 2 raised to the power n times cos of n theta divided by 2, which is what we get, then plus I open bracket 2 plus I, then open bracket 2 cos theta divided by 2, then cos raised to the power n, because this n here can still come here. Remember, it's the same thing I did at this level. Very important, because if I write 2 cos theta divided by 2 raised to the power n, it still come back to the same as 2 cos raised to the power n of theta divided by 2. Okay, and when I multiply it inside this bracket, I get this expression here, from which I can therefore come forward and say that real part, which I want, actually remember, we want the real part of this complex number here. We want the real part of this complex number. We want the real part of 1 plus omega raised to the power n. But since we have 1 plus omega raised to the power n as all of this expression, I can therefore take its real part, which actually corresponds to this 2 raised to the power n cos raised to the power n theta divided by 2, 10 times cos of n theta divided by 2, which is actually what I was looking for. Beyond which I can therefore conclude that this required sum, that is the sum, is actually going to correspond to 2 raised to the power n, then times cos of n of theta divided by 2, then of cos of n theta divided by 2, which was actually what was required for us to prove in the last part of the question. So thank you very much for watching this video, and don't forget to like, subscribe, share the content with your friends for them to benefit from the content as well. So thank you very much for watching this video, and remain tuned for the very next interesting video. Bye bye.